Hello guys, so hopefully you're having a nice day. Uh, this is the video editorial of problem 10 of November Long challenge. The name is Convex Hulk, right? Convex Hulk. Yeah. So, brief introduction about myself. I am Istasis Mishra. I'm a fourth year undergraduate at IIIT Hyderabad. I have been to ICPC regionals twice in my first and second year, and I've represented India in IOI 2018. So I'll just get right into it right now without wasting any more time. So yeah, convex Hulk. So let's try to understand what the problem means. Yeah, before that, prerequisites for this problem, you do need to have a knowledge of computational geometry and also how to find the convex hull of n points in O of n. So I'll be using the algorithm to find the convex hull of a set of points in O of n as a black box. So to understand this problem, before that, let's, like, if you already don't know this algorithm, you can still try to understand how the problem works. For that, I'll briefly explain what a convex hull means. So let's say you have a set of points like this, okay? Convex hull means if you, let's say, had a rubber band that went like this, and suppose the black points that we have, they are the set of points that you have. So imagine this gray thing as a rubber band. So the rubber band will naturally shrink, right? So what will be the final form of this rubber band, right? It will be something like this, right? Right? So that gray line or the gray shape is known as the convex hull of these 5 points. Okay. So let's look at what the problem is asking. So let's try to understand the problem now. So you have a set of P points on a 2D plane, like the black points. So you have this move called Hulk Smash, which takes that set of points P and creates a new set of points P dash. So from P, it makes P dash, right? So I'll just write P dash in red so that it's easier for us to distinguish between the two. Yeah, so initially, so how do you construct this P dash? So initially P dash is empty. Now, for every point Pi and Pj, such that Ij are not equal, you add the midpoint of Pi and Pj to P dash. So for this and these black points, you'll have a point in P dash which will be their midpoint, right? So similarly, you'll have midpoints of every pair of point. So these 2 points will have their midpoints here, 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 here. Then midpoints of the diagonals as well, which will be here and here. So all these red points, so there are 5 points, right? So there will be 5 C2 red points, which is 5 10, I think. So 1 2 3 4 5 6 7 8 9 10. So we have all 10 red points in P dash. You need to find the number of points that lie on the convex hull of P dash, right? So what will the convex hull of P dash look like? Something like this. Right? So this will be the convex hull of P dash. What you need to find is the number of points that lie on the convex hull of P dash. So what does it mean for the point to lie on the convex hull? It means that if you remove that point, the convex hull changes. So for example, this point is not lying on the convex hull, because if you remove this point, the convex hull will not change, right? the orange convex hull will not change. So what will be your output for these set of black points? Your output will be 5, right? Because you have 1, 1, 2, 3, 4 and 5 points. Removing any of these 5 points will change the convex hull, but apart from that, the convex hull does not change. Now let's take a look at the constraints. The points, the coordinates of the points lie from minus 5 into 10 power 8 to 5 into 10 power 8, right? So that's this one. So let's change to black again. So yeah, so it's this one. Sum of n over all test cases do not exceed 2 into 10 power 5. So the number of points do not exceed 2 into 10 power 5. Okay. So yeah, so for this problem, you'll need to make a few observations, right? So take some time, try to, like, if you did not understand the problem during the contest, pause the video now, try to understand the problem, try to think of a solution on your own. If you can't, continue on from here, because now I'll be discussing the solution, right? So for this problem, you'll need to make a few observations. First observation, look at the midpoints of two consecutive hull points. So this and this. So these two are consecutive hull points, right? In P. So look at the midpoint of that. It does lie on the hull of P dash, right? All the 4 midpoints. So there are 4 points on the convex hull of P, and all the 4 midpoints of the consecutive hull points of P do lie on the convex hull of P dash. So that is our observation 1. Observation 1 goes something like midpoints of consecutive convex consecutive points that lie on convex hull of P lie on convex hull of P dash. Okay. So second observation, the midpoints of the non-consecutive convex hull points. So imagine your convex hull is something like this. Okay, so your convex hull point goes something like this, right? So the consecutive midpoints, this and this, will lie, but what about this point? This point will not lie in the convex hull of P dash, right? Because these 2 points will already be a part of the convex hull, right? These 2 points will already be part of the convex hull. So the midpoints of non-consecutive convex hull points of P will not be lying on the convex hull of P dash, right? So that is our second observation. Midpoints of non-consecutive points that lie on convex hull of P do not lie on convex hull of P dash, right? And third observation, if you look at the midpoints of 2 non-hull points, so let's say there is a black point here also, right? So these 2 black points are non-hull points of P, right? So their midpoint, which will look something like this, will obviously not lie on the convex hull of P dash because it will be completely inside. So that should be obvious. Is that obvious? Try to think about this, right? Midpoints of two non-hull points of P will not be a hull point of P dash, right? So that is our third observation. Midpoint of two non-hull points in P do not lie on the convex hull of P dash. So these three observations, try to get through, try to understand what these three observations mean. Okay. I did explain each one of them. Try to replay it if you don't understand. And the final observation, the most difficult one. So you can see there are more points, right? So from these three observations, you can only make out that the what are the points in P dash that lie on the convex hull. Only the midpoints of the consecutive hull points of P? No, right? There are more points. So point number 3, if you look at, point number 3 is not the midpoint of consecutive hull points. It's actually the midpoint of this point and this point, right? Point number 3. So this point and another hull point, right? So fourth observation, I'll just be giving it away. Just try to understand what it means. For 3 consecutive hull points of P, A, B, and C, the midpoint of a point small p and B does not lie on the convex hull of P dash if small p lies outside triangle ABC. Let's try to understand what our observation 4 even means. Okay, so let's say you have 3 hull points, 3 consecutive hull points of P, right? So these 3 black points lie on P, right? And so since I'll just draw the hull once, and the rest of the hull is looking some way. We are just considering these 3 consecutive hull points, okay? And we are naming them consecutively A, B, and C. A, B, and C. Now, I'll just make the triangle okay. Now, let's look at the midpoints of AB. So midpoint of AB is this, midpoint of BC is this. So let me just draw it a bit more properly so that, so let me draw B a bit here so that the triangle is bigger and it's easier to see, right? Okay, so let's look at the midpoint of AB and the midpoint of BC, and there will be a midpoint of AC as well. Okay, all of the red points will be points in P dash. Okay, so let's locate another point P, small p. So let's say our small p is outside this triangle. So what does that mean? Where will be the midpoint of P and B, right? Midpoint of P and B will lie somewhere here, right? So if you join this, so let me draw the convex hull of P dash in orange, right? So this line will be a convex hull, is prospectively, tentatively a part of the convex hull of P dash, right? And this will go somewhere. Okay. Now, if small p lies outside this triangle, there is no way. So, when can the midpoint of small p and b be on the convex hull of P dash? Only when the midpoint lies somewhere in this area, right? For the midpoint to lie in that area, small p must be inside the triangle at least. Is that correct? Try to understand. For the midpoint of small p and b can be a hull point of P dash only if the midpoint lies in this area that I have shaded. And when will the midpoint, so if small p is outside the triangle, the midpoint will never lie in that area, so it will not be part of the convex hull. That is exactly what the observation is saying. For 3 consecutive hull points of P, A, B and C, the midpoint of a point P and B does not lie on the convex hull of P dash if P lies outside triangle ABC, right? If it lies inside the triangle ABC, then also there is no guarantee that it will be convex hull, but it may be, right? But if it lies outside, for sure you know that the midpoint will not be a part of the convex hull, right? So how many such midpoints will we consider? So if you look at any shape, okay, yeah, let's make a convex shape. Right? So assume this hexagon is your convex hull, right? So this is a possible convex hull. For example, this cannot be a convex hull, right? A convex hull will be looking like this. So if you look at all these B's, so if you make this B, the triangle will look like this. So let me just draw it. Yeah, the triangle will look like this. You consider this B, the triangle will look like this, and similarly you can make this thing, right? Did I miss one? I consider this B, this B, this B. Yeah, this was left, right? So all these are your triangles, right? Yeah. So how many triangles can, so it's difficult, so you might lose track of how which are the triangles, right? So I'll just try to shade them. This is one triangle, this is one triangle, this is one triangle, this is one triangle. So try to observe, like it's kind of difficult to see here. Let me just draw this whole thing again. I'll use a less number of points now. Okay, so I'll just make it a square. Okay, so this is a triangle and this is a triangle. That is it, right? So this area, right? If you consider this B, I'll draw them using different colors. So this is one triangle, right? Now let's use this. This is a triangle, and let me use green. This is a triangle. So do you ever see more than 2 colors overlapping here? No, right? Only 2 colors overlap. So this should make sense, because why? If it's something like this, right? So you'll have a triangle like this and a triangle like this. This part is the overlap, right? And this part will not overlap with any other triangle, right? Because the next triangle will start from here and from here, right? So this part, this area will not be overlapping with any other triangle. So at most only two triangles can overlap, right? So how many parts can this, how many triangles can the small p be a part of? At most two, right? So for a particular b and for every other point inside the convex hull that you can consider as p, that p will be a part of at most two triangles, right? Not more than that. So each p will contribute like maybe. So for each p, if it lies in the triangle, then you can say that maybe this is a convex hull, maybe this lies on the convex hull of p dash. You are not sure, right? So how many such points will you be taking into account? At most 2 into n, right? So for p you can consider this as b, and for this p you can consider this as b again and make another triangle, right? For this p you can consider this as b. Can you? You can consider, you'll try to consider and see if that contributes, but this p can be inside at most two triangles because more than two triangles do not overlap on any area. So each p will contribute two midpoints that will be that have the possibility of lying on the convex hull of p dash, right? Two endpoints. So, and these four are the only observations you have to make, right? So what are the possible hull points of p dash? Midpoints of consecutive hull points of p, and the fourth observation ones. Fourth observation ones will contribute O of n points, and consecutive hull points, how many points can there be? Exactly n midpoints will be there, right? At most. So O of n points here. So overall you have O of n points that have the possibility of being hull points of p dash, right? And since you have O of n points, what can you do? After you figure out all these points, you put them in one set, right? Put them in one set and find the convex hull of that in O of n, right? Then you know all the hull points of p dash. Basically you are not considering the points, midpoints of non-consecutive points and midpoints of any random non-hull points of p. You are not even trying to consider it. If you do consider it, the complexity of finding that finding the hull points will be of n square, right? Because for every pair of points you'll have to take the midpoint and then you'll try to find the convex hull of that. And if there are n square number of points, like nc2, right? If there are nc2 number of points, which is O of n square, if there are O of n square number of points, finding the convex hull will take O of n square time, right? But you reduce that to finding the convex hull of O of n points. So at most 3n points, right? You will not find, you will not take into account more than 3n points. Now, the final part, the final thing you need to think about in this algorithm is how do you figure out this p, right? So how many points, how many hull points can there be? So let's assume there are n by 2 hull points and there are n by 2 non-hull points of p, right? Capital P. So each of these you can consider the b, and for each of these you'll have to consider these p. Each of these can be considered b, each of these can be considered p. So if you try to pair them, you are again running into an O of n square algorithm to find if they are in the triangle or not. By the way, checking if a point lies inside the triangle or not can be done using cross product. So that comes from the knowledge of basic computational geometry. I will not be covering that in this video, otherwise it will become too long and it will become like I'm teaching a topic on its own and not actually explaining the problem itself. So having the idea of basic computational geometry and knowing how to find a convex hull is a prerequisite to solving this video, to solving this problem. Okay. So yeah, how do we what do we do about this? So for this triangle, right? So assume like this was my, okay, let me just draw it again, right? So A, B, C, right? So let's look at the, let's cut it at the vertical point, okay? Now P, you don't, if a P lies outside that vertical area, then you don't even need to consider it, because you know, okay, this will not lie in this triangle ever. It's only the P's that lie here inside this vertical area that you need to consider. If they lie outside, you know, okay, they are not in the triangle. If they lie inside, they may be in the triangle, they may not be in the triangle. So you need to consider all those points, right? So if your let me just draw it properly. Drawing a convex hull is kind of difficult. So let's say this is your convex hull, okay? So first you'll consider this as B, okay? And your vertical point will be like this, okay? Then you'll consider this as B, and then your vertical points will be the minimum x and the maximum x, okay? So the minimum x among A, B, and C. So if this is B, then this is A and this is C, right? And the minimum x value will A will have the minimum x value, right? And which will have the maximum x value? B. So you only need to consider this, right? And you don't need to consider anything else. And then you consider this as B. So this will be your A, this will be your C. So minimum x, C, maximum x, A, right? So you only need to consider points in this area, right? And then you move again, this and this, right? So you can kind of see that each point will be considered O of n number of times. So each P, this P will be considered. So for example, this P will be considered all the times, but you can kind of like understand the complexity won't be O of n square anymore. You are not considering every P and B pair that is possible, right? Like it's kind of difficult to give the intuition about this right now, but this is how you solve this problem. So you only consider the P's that lie in this range. So what you can do, keep all the non-hull points inside a set, right? Find the lower, so find the minimum x and the maximum x by doing like minimum of A, B, and C x, maximum of A, B, C x. Then what you do is do a lower bound, upper bound. If I find the lower bound and the upper bound in that set, and just iterate through those points. You don't need to iterate through all the points, and each point will be considered like overall the points will be considered O of n times. So this you need to have an intuition of your own to understand. I'm not sure how to give the intuition of this. I kind of can try to understand. So if this is your P and you are only looking, so let's say this is your convex hull. So you'll look at these, maybe your vertical point when, let's say if your V is in the lower envelope, right? If B is in the lower envelope, this will be a point, this will be a point. You'll go like this, like forward. Then eventually you'll come up and then you'll go backward, right? So this P won't be considered with many B's, right? So that is the best way that I can give this intuition. Other than that, you need to understand it. So in O of n, you find all the points that can be hull points of P dash, and finally in O of n, you find the convex hull of all those points, and that is your answer. right? So hopefully it's kind of clear. Hopefully, I can't be sure. Okay, but yeah, these 4 observations are the crux of this problem. Okay, so now let's move to our implementation. Okay, so this is your testers code. Yeah, this is your testers code. You can see all the asserts and everything here. This is just input, 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 input. Cross product, I'll not explain. This whole thing is, so we have created a struct called point, which has, you know, our x, y, our operator equal to, operator less than, defines all of that. Hopefully you guys know C++. So yeah, you define a struct called point, you operator overload the equal to and the less than equal signs, less than sign. So why do you need to overload it? So that you can store it in a set, right? Otherwise you can't store it in a set. It needs to be define this less than operator. Convex hull, what this is doing is, given a set of points P and f equal to 0, so this is kind of like multi-purpose convex hull. So you can just copy paste this part in any problem. You don't need to write the convex hull function every time. So this is a flag. Making it 0 means it will include collinear points. Let me just explain what that means. Yeah, let me just quickly explain what I just said means. Yeah. So if let's say your points are something like this, so your convex hull, so these are your points. So your convex hull look like this. So you can see this point, and this point. These 3 are collinear points. The middle point, do you include in the convex hull or not, right? So all that f is doing is, if you set f equals to 0, it will include the collinear point. If it is 1 or anything else, anything positive, then it will not include the collinear points. Okay, so yeah, all this convex hull is doing, function is doing, is in O of n, it is finding the convex hull of a set of points capital P. Okay, so yeah, for each test case, you take n, so all of these are asserts. So yeah, again input, more input. Yeah, so copy hull is the vector that sorts, keeps all the points in a sorted order. Why? Then you find that left and the right index for each triangle ABC, right? In ABC, for each triangle you find the lower and the maximum index of the points that you need to consider. So that is why you use this copy hull. So vec is the original vector of points P, copy hull will be the sorted points. Okay, so you sort the copy hull thing initially, and yeah, you find the hull. So hull will be equal to convex hull of vector, right? So you find, so hull stores the convex hull of P. The VEC is the original P, right? Not P dash. And NPTS will be storing all the points in P dash that have the possibility of being the convex hull. Okay. Yeah, init x is storing all the x values, and yeah, finally this loop is doing all the work, right? So this loop will be pushing points into our NPTS. So firstly, point P will be midpoint of the ith point and the I plus 1th point. We do mod m because we also need to consider the nth point and the first point of the convex hull, right? So every consecutive convex hull, so point P will be the midpoint of consecutive hull points of P. You just push it after calculating it. So x plus x by 2, y plus y by 2, right? You just push it. Now low will find the minimum index. So minimum between A, B and C. So you consider the ith point as B. If the ith point is B, then the I plus 1th point will be C and I minus 1th point will be A. And you do this plus m mod m thing so that it just loops back, right? So yeah, this min is finding the minimum x value between A, B and C, right? So this is B, this is C, and this is A, the x value of A. So that is why you do this dot x. So low will find the minimum x value, high will find the maximum x value. Then IDX1, you are doing a lower bound on the low value, right? So the minimum index in the copy hull array, right? The minimum index in the copy hull array that we need to consider, it is IDX1. The maximum will be IDX2. So you do a lower bound on low, you do an upper bound on high. Fine. Now J will go from IDX1 to IDX2. If copy hull is equal to hull, you don't consider it. Otherwise, you take the midpoint and you push that push the P, right? And then you just sort all the so here you're not actually checking if they're in the triangle or not. You are just pushing all the points that lie in that area from minimum to maximum. So even that works, right? Even that will create O of n points overall, right? Because it's taking O of n time to iterate, that must mean that even after putting all the points multiple number of times, you will at most put it, you'll have a O of n size of array. This NPTS size will be in O of n. So first you sort it, then you do a resize of unique. So what this line is doing is that all the duplicate points it's removing, right? So each point might be there twice or thrice. So this line will just make it occur once. Final hull will be our convex hull of NPTS, and you're doing 1 because you do not want to include the collinear points, right? You do not want to include the collinear points, and that is the requirement of the problem. So you pass F as 1. And finally, see here you did not pass F as 1, right? Yeah, because you need to consider the collinear points here. And finally, yeah, finally you just need to print the size of the final hull, right? Hopefully the problem is clear now. I have explained this. So I think this is the setter testers code. You can head over to the actual editorial of this problem that includes setter, tester, and the editorialist's code, all of them. I hope you enjoyed solving this problem and hope the whole contest in general. And yeah, I'll be seeing you in the next editorial that I make. Thank you for watching. Bye.